Hello everyone, I am Matthew and I will present our work Enhancing Shallow Neural Networks for Fourier-based information fusion for stroke classification. As we know, deep learning-based models have been massively studied and applied to daily tasks, mostly due to its remarkable accomplishments achieved. However, some applications suffer from a low volume of labeled data, which can dificultate the learning procedures of deep neural networks. An important application stands for the detection and diagnosis of cerebrovascular accidents, aka stroke. Also, the correct stroke diagnostic has a significant impact since it can lead to several degrees of sequelae, as physical dependencies or depression. Most of the related works employing convolutional neural networks, CNNs, which may be challenging to be trained and depend on large volumes of data. Nonetheless, the main objective of the proposed work is to detect and classify stroke using a small dataset and less complex neural networks, such as the restricted Boltzmann machines, RBMs, and a new RBM-based methodology employing the Fourier transform. The RBMs are stochastic neural networks based on physical principles of energy. They are composed of two layers of neurons or units, one visible and one hidden, capable of modeling problems through unsupervised or supervised learning. Here we have a schema in which the V vector stands for the visible layer and 8 vector stands for the hidden layer. And as I said, V and 8 are the visible and hidden binary units, but if the input data that the visible layer receives are normalized in a Gaussian distribution, we can use continuous units, and the W stands for the weight matrix. The Fourier transform. Its postulation indicates that any periodic function can be expressed as a sum of sines and cosines of different frequencies, each one weighted by a different coefficient. Here we have the formulation of a general Fourier transform for a two-dimensional space with x and with u and v coordinates, and r and I stand for the real and imaginary components, respectively. U and V represent the two-dimensional matrix coordinates, and phi is the phase angle. The magnitude and the phase angle of the input signal is defined by the following equations, respectively. The stroke, or cerebrovascular accident, is characterized by an injury that abruptly strikes the brain tissue. It is mainly caused by changes in the blood supply to a certain region of the brain, resulting in loss of reduction of its function. The stroke can be classified in ischemic, most common, characterized by the blockage of a vessel responsible for brain irrigation, and hemorrhagic, characterized by a rupture of a blood vessel in or around the brain. Here we have the brain and example of the hemorrhagic stroke, in which we have the rupture of the blood vessel, and here we have the ischemic stroke, in which we have the blockage of the blood vessel. Several works deal with medical applications, however, Pereira et al., here is the reference, employed CNNs to detect and classify CT images of patients with or without stroke. The authors obtained relatively high accuracy rates regarding stroke classification using CT-based images. Also, the authors pointed that medical images are hard to obtain and harder to label, which may lead to small databases, as the one made available with 300 images. In front of the difficult to train deep neural networks with small databases and the open database provided by the authors, such work was employed as the baseline for our proposed approach, which is the multimodal RBM. The multimodal Fourier-based RBM proposed to represent information in different domains through the Fourier transform. The use of information fusion for the training of RBMs can successfully be applied to the problem of stroke detection and classification, since the images can be transformed. Here, on the left side, we have a schema of two RBMs, in which the first one receives the original images, the CT images, in grayscale, with a Gaussian input. And on the right RBM, we have the input being the Fourier transform of the same image with the phase angle. Both networks are trained simultaneously, and after the unsupervised pre-training, we can fine-tuning all the weights using backpropagation. On the right side, we have the process of applying the discrete Fourier transform on the CT image, and we can obtain the phase angle and the magnitude. The two images generated from the Fourier transform can generate the first architecture named multi Fourier-based RBM phase, multi Fourier-based RBM magnitude, or both images feeding two different RBMs on the same time, which is phase and magnitude. The dataset have 25 CT scans of the brain comprising patients with healthy brain, the first image, ischemic stroke, the middle image, and hemorrhagic stroke, the last image. The total number of images is 300, where the first 100 depicts healthy brains, and the last are equally divided in hemorrhagic and ischemic stroke. The authors also suggest splitting the data in two ways: 50-50, which means 50% of the total data for training and 50 for test, and 75% of the total samples data for training and 25 for test. The original images have been rescaled to 50-50 pixels. Also, they were grayscaled and normalized according to a standard Gaussian distribution with zero mean and unity variance. The methodology regarding the models, we have the pre-training and the fine-tuning phase, in which the pre-training have a small batch size with 10 samples and 50 epochs. For the fine-tuning phase, we employed the Adam optimizer with a small learning rate and another 50 epochs with a larger batch size with 60 samples per batch. Here we have the names of the models employed, which Gaussian RBM stands for only original images feeding a Gaussian RBM. The multi-Fourier RBM based with P stands for the Gaussian RBM and another RBM to process the phase angle from the Fourier transform. The multi-Fourier-based RBM magnitude stands for Gaussian RBM and another RBM to process the magnitude from the Fourier transform. And finally, the multimodal Fourier RBM phase and magnitude stands for the three models together to compose the final model. We have the hyperparameters employed, and it's important to highlight that all these hyperparameters was empirically chosen in previous experiments, and we can jump to the results regarding the two splits proposed by the authors and the architectures. Here we have the accuracies, in which the bold values stands for the best ones according to the Wilcoxon test, and we can notice that for the 50-50 split, the first one, the Gaussian RBM overcome all the models, surpassing the CNNs 1 and 2 employed on the work of Pereira, and the multimodal Fourier-based models proposed in our work also overpassed the baselines, the CNNs, but not overpassed the simplest architecture, the Gaussian RBM. However, all models employed, all RBM-based models, have lower standard deviation than the CNNs employed in the work of Pereira, which is interesting, since we can reproduce the results with a more accurate rate. For the second split, the 75-25, we have another pretty interesting scenario in which the multi-Fourier-based RBM with the phase angle being the best model, over all the ones underlined here, and the 50-50 is underlined here. And again, all the RBM models have the lower standard deviation over the baselines and the higher accuracies regarding this split, which also is pretty interesting since the phase angle from the Fourier transform seems to incorporate important pieces of information for our model, for our multimodal model. In this image, we have the convergence, or better, the accuracy evolution of the model, of the proposed models, and we can see that multimodal models for the 50-50 split are a little bit more unstable on the first 30 to 40 epochs, and for the 75-50-25 split, we have a more stable behavior for the accuracy evolution. This can be explainable by the fact that we have more data to train, 75% of the data, and indicate to us that the multimodal models can be very useful, but it is still requires more data to obtain the better results. Here we have parameters analysis over the models, and the most useful information here is the ratio that correlates the total number of parameters of the baseline models, CNN1 and 2, against the RBM-based models. The RBM-based models have approximately 53 times the number of the parameters of this simplest CNN employed on the work of Pereira. However, as we saw, the results was pretty greater than CNN, and again, this result is more interesting for the CNN2 that have far more parameters, and the RBM-based models have 0.08 times the total number of parameters of the CNN2. In conclusion, this paper, we proposed a novel approach based on multimodal RBMs employing the Fourier transform on CT images to feed neural networks applied to stroke detection and classification. The experiments conducted over the public dataset confirmed the sturdiness of the models, achieving state-of-the-art results in front of the work from Pereira et al. Moreover, it's important to highlight that multimodal models employing phase angle from Fourier transform improves the stroke discrimination better than magnitude. Regarding future work, we intend to deeply study the possibility to make an auto-data augmentation with the employed networks, as suggested by Hodder et al. Also, we intend to use convolutional RBMs rather than RBMs, even with more parameters. Thank you.